Hello, I'm Cheng from Microsoft. I will present our paper ASAP, Automatic Synthesis of Area-Efficient and Precision-Aware CGRAs. The work is done when I was at PNL and collaborated with University of Utah and Harvard University. All right, the background comes first. Emerging applications can tolerate different precisions or number formats. For example, machine learning applications nowadays are powered with different number formats like floating point 16, floating point 8, NVIDIA's TensorFlow 32, Google's BFlow 16, Microsoft floating point, and so on and so forth. Besides machine learning, the other application domains have their own precision requirements. The high-performance computing domain needs guarantee the accurate result of these scientific applications, which might require the most reliable precision support. On the other hand, the embedded domain might be able to trade off the accuracy with the application execution latency to provide real-time response. This trend has also been shown in the hardware. For example, the FPGA and NVIDIA's GPUs have started to support different number formats to accelerate specific applications. However, existing CGRAs are still empowered with either fixed point or floating point number format, which limits their potential to trade off the accuracy with power and area efficiency. Meanwhile, designing a CGRA with a specific number format or multiple different number formats adapting to an application domain involves enormous hardware-software engineering effort. For example, we need model the CGRA in Verilog for synthesis, write a mapper to map the application onto the modeled CGRA, and before that, perform design space exploration to determine which type of number format can satisfy the application domain, also including what the processing element and network topology the CGRA should have, and what the loop level optimizations should be applied on each accelerated application, and so on. Therefore, we propose ASAP, an automated framework to design a CGRA for a specific application domain with the consideration of precision and number format support. I will use a motivating example to show what benefit we can get from supporting different number formats in a CGRA. The figure shows the sparse matrix vector multiplication code with its data flow graph. I eliminate the branch related to the for loop for simplicity. From the figure, we can see that the multiplication and addition operations actually compute the final result, and the number formats applied on those two operations would affect the result accuracy. The rightmost figure shows what it would look like if the DFG is mapped onto a 2x2 CGRA. We can see that the entire DFG can be done in 3 cycles, which means each iteration of the SPMV for loop takes 3 cycles for acceleration. The different colors in the CGRA tiles indicate different number formats are supported on those tiles. Instead of supporting floating point 32 across the entire CGRA fabric, specifying the number formats on certain tiles can significantly save the chip area and power. For example, supporting BFlow 16 on the tile executing multiplication and supporting floating point 16 on the tile executing addition can improve the CGRA's area efficiency with trivial accuracy lost. ASAP is an automated framework to design a CGRA for a specific application domain. Before diving into its design exploration details, I would like to show ASAP's template architecture, which is used to perform the design space exploration. The ASAP CGRA template contains multiple tiles that are interconnected with a king mesh network. Each tile contains a crossbar, a configuration memory, a set of registers, a format converter, and a set of functional units. Note that the functional units can support a specific number format. This template architecture is used by ASAP's design space exploration engine and can form any type of CGRA design as shown in the rightmost figure. In other words, the design space exploration engine can remove certain channels in the topology and choose specific functional units supported with certain number format to construct the most area-efficient CGRA design for an application domain. The table shows all the factors that ASAP would explore, such as tile count, topology, functional unit type, data memory organization, and the number format supported in each tile. Besides these hardware design factors, the software-related tiling factor and enrolling factor can also be explored. This slide shows the workflow of the ASAP framework, which includes the loop transformation, DFG generation, operation fusion, DFG mapping, design evaluation, a hardware-software co-design engine, and CGRA generation. Loop transformation applies appropriate loop-level optimization such as loop tiling and loop unrolling on each target kernel given a specific application domain. Then the DFG can be generated for each application kernel. Operation fusion can be applied to combine the most common compute pattern appeared in the DFG. For example, multiplication followed by addition would be probably fused as a MAC operation, given the machine learning kernels, as those two operations always appear in a pair. Afterwards, the updated DFG is mapped onto a CGRA design for performance, area, and power evaluation. The hardware-software co-design engine then looks at the evaluation report to determine how to optimize the CGRA design and the loop-level transformation. For example, if it may shrink the design by removing some tiles if the area budget is exceeded. It may also change certain tiles supported number format with higher precision if the kernel's result accuracy is lower than a threshold. The design space exploration is implemented based on a simulated annealing algorithm. It starts from a single tile CGRA design and runs iteratively until the design is converged given a specific target like area efficiency or power efficiency or pure performance with certain constraints such as accuracy. Afterwards, the optimized design will be fed into the OpenCGRA to generate the synthesizable Verilog. I'll use a walkthrough example to show how the hardware-software co-design engine works. Given an application kernel, the DSE engine starts from a single-tile CGRA model, iteratively enlarge or prune the design, and evaluates the performance, area, power, accuracy, and so on. If the area budget is exceeded, the data memory could be decreased. Correspondingly, the application kernel should be appropriately tiled to be fit into the shrinked data memory. The engine might also enlarge the design if the performance can be improved by providing more compute resources. Meanwhile, the kernel loop needs to be unrolled accordingly if the enlarged procedure leads to underutilization. Moreover, if some compute pattern in the kernel DFG can be fused, the DSE engine can prune the design by replace the general functional units in some tiles with special functional units to save area and improve the performance. Finally, if the application domain is not sensitive to the accuracy lost, the DSE engine can try to manipulate the supported number formats in each tile to improve the area efficiency. In this way, we make the design space exploration precision-aware. Such DSE procedure runs iteratively until the design being converged as an optimized one in terms of a customizable target such as area efficiency or power efficiency. So here comes the evaluation. We evaluate the ASIP in 3 application domains: scientific computing, embedded domain, and machine learning. Each domain contains a set of representative kernels. We set unique accuracy threshold for each domain in this evaluation. For example, scientific computing normally requires accurate results, so it does not allow the accuracy threshold to be lower than 99.5% in this domain. On the other hand, machine learning domain might be able to tolerate trivial accuracy loss, so 98% is given in our evaluation. We also evaluate the area and power statistics for the functional units with different number format support. We can see that the fixed point 16 and the B-flow 16 have lower area and lower power overhead than the other formats in both adder and multiplier. The figure shows the performance improvement of the optimized accelerators generated from ASAP compared against the manually designed baselines across different collections of workloads. We can see that ASAP improves the power efficiency or area efficiency by from 3.2 to 5.8 times in different application domains. We also evaluate the efficiency improvement under different accuracy requirements. We can see that the power efficiency of the optimized CGRA for embedded domain can be significantly improved when the accuracy threshold is relaxed. Actually, ASAP's design space exploration takes time, which might take hours to converge. Fortunately, if users can feed a multi-tile design as the start point for the DSE engine, the execution time can be significantly decreased, but this is based on the experience of the users. Here is the takeaways. ASAP is a hardware-software co-design framework for the automatic synthesis of optimized coarse-grained reconfigurable accelerators with the consideration of accuracy starting from a set of kernels of interest. ASAP employs a generic architecture template that allows building any type of specialized CGRA and performs the DSE through an architecture-aware simulated annealing optimization algorithms. This wraps up my talk. Thank you.